Welcome to lecture 31, which is really the first lecture now in the second part of the class. The first part is the 2D space groups. Now we're just preparing for development of the 3D space groups, and then we'll start developing them. And then finally, the last part of the course will be tensor properties of materials. Basically, after having these crystallographic space groups, we'll use tensor notation in order to represent various properties. So in starting the second part, we will need to do a little background here, and that's what we're doing in this lecture. So let's review what we actually did to do the 2D space group so we can see the analogy for the 3D. So if you recall, we had basic operations. We had translation, reflection, and rotation. I guess if I did operator, I should have. Those are the operators. And we found out through combination theorem, that was the one where we said, remember we had PT filling space for translation vectors. And that resulted in having groups that were n. So we had, remember, an n-fold axis of that could fill space because of our little combination theorem. And then we said, okay, this means that there's only certain lattices that are compatible with those rotations, because these are point groups. We developed these point groups, which are pretty simple. They're just rotation, and then we put them into the lattice for this behavior, and that resulted in the 2D nets, which was the the primitive parallelogram or oblique, whichever you wanted to call it, the square. When we use the mirror plane on this instead of just the rotation, we ended up with a rectangular and centered rectangular, right? Then we said, okay, we'll take our rotational point groups that are compatible with the lattice and the lattices that are compatible with those rotations. And we said, okay, let's put them together. Oh, and we added one more thing. Remember, there's a two-step operation. So this is the basic operations, two-step, which in 2D we had glide. And that gave us then the 17 2D plane groups or space groups. So now we're going to essentially go through a very similar idea. So we have our basic, which is going to be T sigma A alpha, but of course now we have inversion. And, essentially nothing changes in the sense that we still have our n-fold point groups, one-fold, two-fold, three-fold, four-fold, six-fold, right? The only difference is that in 3D, we have to consider axial combination. So if you think about our 2D case, we just have these rotations and then we look for other symmetry elements that were induced under various cases, but we didn't have to have, um, you know, a strategy where we artificially put in multiple rotations and had to have them compatible with each other. We would put in a rotation into a lattice and then we would add other elements and look for the symmetry elements. And that's the way that we made it compatible, right? Here, that'll be a little complicated. And so right up front, we want to look for the basis set of rotation elements in 3D that are compatible. So for example, if I have a six-fold axis, I can definitely just say, oh, I've got these again. However, in 3D, if I want to add some other rotational element, actually I need some new um, way to deal with having a third axis, other axes be compatible with a point group because they're going to spin the motif around and that whole pattern needs to be self-consistent. So the way we're going to do that is there's an Eulers construction that's going to be useful. And so we'll use that to get 11 axial point groups in 3D. And then if we use inversion, that's going to create the 32 3D crystallographic point groups. Okay. Now there's going to be other two-step operations that we add that are going to go into here. Here I said we have these glide operations. We still have glide. And you've already had a little bit of exposure to them in homeworks. So roto-inversion and roto-reflection are the new ones right now. For our point groups, we're going to add something later to achieve finally our three-dimensional crystallographic space groups. But for the point groups, we're going to add these guys in addition. So we add the inversion, we add these other ones, and that gives us our 32 3D crystallographic point groups, which then of course we can add to our lattices, which will be based on our 2D, right? So, we're going to later combine these two plus other things. That says other, if you can't read that. And that is going to finally give us our 230 3D crystallographic space groups. And instead of going through some of the, but this is basically the idea. So you can see here our first task then is to say, all right, I have certainly the simple case where I have no other rotational axis in 3D. So already I'm going to have a bunch of groups that pass right through here, and they're going to be part of our 3D groups. All they're going to be are same things, rotation with nothing else in 3D, right? Just that one central rotation. So pretty simple. And they're going to pass, right through, and we're not even going to think about them too much. Then we have the case where we use Eulers construction to create axial point groups, and that's what we're going to do next. And we'll see, of course, that actually forces us to deal with inversion, and then later we'll add in these two in order to arrive at that. So let's start with this first step. So the problem that we're actually trying to solve is one where I have a rotation in the 3 dimensions, but like I said, if I have no other rotations, then it's pretty simple, straightforward. I just have to make sure that everything else around here has the motif is compatible with this rotation. That's about it. However, in 3D, I will want to, of course, look for other possibilities. Now, in 2D, you can think about it as these things didn't converge at a point. We just had separate axes in space. And we cut through them. We just had to make sure that all these rotation elements, this guy's rotating around beta, this guy's rotating around alpha, and we just had to make sure that in some plane, the motifs made sense, right? So here it's a little bit different. If I add a rotation here, I have to make sure that's compatible with that. Now it turns out, as we suspect, if I do rotations here, that's equivalent to and therefore compatible with another rotation. And you can see what's happening here because you all know that, like if I look at a cubic crystal, right, there's things like twofold axes, like a twofold axis can come out of here, and you have a fourfold axis here, a fourfold here, etc., and a threefold coming out of here. And so we can automatically see that for some sort of motif related to a cube, these all can be compatible with each other, right? And they're all emanating from some central point. So you can see that in 2D, these things are more or less separate because, we just had to make sure that all the in-plane stuff made sense, whatever the pattern was. Sorry, I should probably, there's another one of those, and then this one had some relationship to them, and we looked for these other symmetry elements based on putting in some fundamental rotations first and the lattices, etc. Here, they're in 3D all at a point actually, so it makes things more complicated, right? So I put in one guy, and then I want to know which ones are compatible. Well, if I put in the other one, then it automatically means there's an equivalent rotation. And so this construction is going to be key in finding out this axial compatibility, if you will. Some notation is the one that's opposite B, which would be the angle between A and C, we call B, little b. And then the angle between A and B, we call C. And of course, the angle between C and B, we call A. So these ABCs are actually angles, okay? Now the construction that is used to help See, all this is essentially trigonometry on a sphere, because when you're dealing with something like this, you can see here the square doesn't really help us because it's not, uh, these three axes at a point automatically suggest we should look at a sphere. And it turns out, and there's background on these things, uh, put this on a sphere. B penetrates this sphere at some radius, and if we keep the radius the same for all of these, let's imagine that it's penetrating something like this. Just making this up, but you know, all those radius links are the same here. And we would construct then this, you know, sort of spherical triangle, because it's the same as a triangle except that you're on the surface of a sphere instead of being, um, you know, in a planar arrangement, right? And so obviously, if we're going to look at the relationships and say, well, if I rotate around this one, rotate around this one, we're going to have to be using this sort of spherical trigonometry in order to create those rules. And you can see already one thing that happens is that these links here, that's the same as C, and this is A, which is of course one of the unique things about angles and dealing with spheres. And then this one between these guys, you know, is B. So we end up with a little triangle. And that triangle has, the way I drew it, the C pole coming out and a B pole coming out and an A pole coming out. And it's got length A and B and C, or angle and length, right? And because of this, you know, situation, we can look at analogous expression of a planar triangle. So if you wanted to find a relationship between this angle A, we can use all of the side lengths, the other rotations that we're passing through, and we'll do that. And we're going to find the same thing with our spherical triangle. We're going to have, so very similar expression, except that instead of being the squares like it is in the planar case, in a sphere, we have this law of cosines, and we'll come back to that later. So essentially, all we'll need then, from knowing the compatibility, we need to use this expression later. And you can imagine that we're going to have to use it with all three of them, right? These equivalent expressions. So this is for A, but we have one for B and C. So just to remind you what we're doing here, we're saying we have, you know, some motif that we're rotating around here to some, you know, final position here. And then, you know, we're rotating, so that would be, you know, 1. And then around B, we have to do a rotation of some value. It has the same handedness, of course. And then that says, well, the relationship between 1 and 2 uh, is, oh, sorry, let's see, I screwed this up. So this is after that rotation, and 3 is after that one. And so then there's some rotation here about C that's equivalent, which relates 1 to 3. Okay? So that's basically what we're doing. And again, that's just saying, of course, if I have these rotations in 3D, and those rotational axes are related to a point, which they will be, because they all have to start the same point in 3D. Was that all the action we're talking about is about when these axes hit that sphere, we're going to look at a little piece like this, and we have some expressions like the law of cosines we went over in the last view graph, that if A is a rotation through alpha, and B has a rotation through beta, and C has a rotation through gamma, then interestingly, this angle is alpha over 2, this angle is beta over 2, this angle is gamma over 2. So you can already see that this is a huge advantage now, because once I have this information, thinking about the rotations about these axes, and I've got my triangle with the cosine, law of cosines, then now I might have enough um, information in order to solve for the case where I have rotation, rotation. What is this one? How far away is it? Because that's really what we're after, right? We might say, for example, I want to have a twofold axis. Twofold axis means that alpha would be 180, right? Which means that this would be 90 degrees. And then let's suppose that I had a twofold axis here. Which means that this would be 90 degrees, right? Well, because of this construction now, and the law of cosines, I'm able to do a couple important things. One is if I can look for different options of gamma over 2, I can say, all right, I want this axis to try to be, if this is a twofold and this is a twofold, I can say, well, I want to try, like we did before, let's see if we can make these compatible with these guys or something, right? And then if I do make them work out, then, and don't forget gamma here is always gamma over 2 on the inside that I would use in the formula. So this would be 180 and this is 120, this is 90, and this is 60, but then divide those by 2 in order to get the inner angle here. And that would allow me to identify, importantly, A and B and C, because that would force all of these axes, because remember these are ultimately, some axes that comes back to some point far away. And it defines essentially the relationship of those axes so that the motifs after the rotation are compatible, right? And that's basically the strategy we're going to use for doing this. So Eulers Construction has a very special property, actually, using a trick called polar axes, to the spherical triangles. So we're not going to derive this. It's in a lot of places, but you see here we have our cosine A equals cosine B cosine C plus sine B sine C cosine A, and that was based on our triangle where we had something that looked like this. And so here's just the expression of cosine A involving the angle big A, which is across from it. You'll notice that when we actually use these expressions, we transform them, and that transformation actually allows us to reduce and rearrange so that we can solve three equations once we have Eulers construction, where we have the inside angles, when we have rotations about these axes, alpha over 2, beta over 2, and gamma over 2, it allows us to plug in and get a solution. So without going into too much data and too much derivation, what happens here is that we can take, remember that the BC angle, the BC arc is part of a great circle that's passing through here, right? So we can take the pole, like if I were to draw sort of, this would be a great circle, not this little tiny one, but I can draw a pole that's perpendicular to, the BC great circle, right? And that comes out, we call this A prime. And then it turns out that I can do the same thing for each of these. So the plane, the great circle defined by AC over here, I can draw that, extend it through B. And we're going to call that B prime. The same thing, I'll draw an axis in that's coming out of this AB one, and I'll push it through C, and we'll call that C prime. So it turns out this is called a polar triangle because we form it from creating the poles on each of the three great circles that forms the spherical triangle here. And this polar triangle, the only reason we're doing this is it's got some special properties that allow us to do a math trick. That's it. So there's nothing more significant than that. And when we're talking about rotations around these three original axes in the spherical triangle, what it means is, like, for example, in B here, the length of this arc connecting A prime and C prime happens to be 180 degrees minus beta over 2. And so what happens is that'll allow us to basically, and it's the same thing for this one, this would be 180 minus alpha over 2, and this is 180 minus gamma over 2, and in itself it's a spherical triangle, so it still holds to this guy. And so what we'll do is we'll substitute in 180 minus beta over 2 in for the length of this arc, which this here is B, so put that in, and so we'll substitute 180 minus gamma over 2, 180 minus beta over 2 for B and C, for example, and alpha over 2 for A in this expression. And that'll actually transform these into the form that I'm showing you here, which is cosine of A now is going to equal things like cosine beta over 2, cosine gamma over 2, plus cosine alpha over 2, divided by the sine of beta over 2 times sine of gamma over 2, right? And that's the form that we're going to use now. So just kind of a quick explanation of how do we go from this law of cosines for a spherical triangle to the form that we're going to use in the next view graph. I just wanted to emphasize that that's how it's done. Again, this polar triangle formation, I wasn't talking about rotations, about the axes that are popping up through here, and now I am. And if they had internal angles of alpha over 2 and beta over 2 and gamma over 2, then it turns out that this guy here is 1 minus beta over 2 in this polar construction. And you can use since this is for all spherical triangles, you can use this to plug in here, and it transforms these into a form that then, if we know, like if we fix the rotations that we're doing, like beta over 2 and gamma over 2, we'd set them to, let's say, twofold axes, right? So that would be 90 and 90. Then you can plug in for everything, and we could come up with how far apart the other axes are. So that would define A, how far apart these guys are. So that's what we're going to do in the next view graph. So let's do the beginning example of setting that up. So the law of cosines, we already mentioned that we have this situation here. Then we have these expressions. Now furthermore, I'd pointed out if we have rotations about these guys, as such, there's a way to construct this so we can prove with great circles that those inner angles are those, which of course makes it very convenient because now I can say the following. So for completeness, I've written them out here, and now that we have the relationship from Eulers Construction, you can pretty much solve for these. You know, if I make a little table and I say let's make B possibilities here, you know, I can have no rotation, a trivial, right? It just does nothing. 2, 3, and 4, etc., right? And 6. And then I have A, which can be, you know, 1, 2, 3, 4, 6, etc., right? Then if I look at my little table, the possibilities for here are like 1, 1, 1, and these are not Miller indices, by the way. These are rotations, right? So this represents nothing happening on A axis, nothing happening on B axis, and then C has that possibility. And C, of course, could be a 2, and then C could be a 3, you know, etc. in this quadrant here. So what's going to happen there is that, of course, you can see already that, well, these are trivial and they already will exist because this is the situation I talked about before where there's actually no axes. A and B don't do anything and we just have C. Those are going to be valid point groups, but they don't use anything we just talked about, right? Because you're not rotating around two of them, right? So the next category, if you start looking at these ones that are not on the diagonal, you'll have like 1, 2, 1, 1, 2, 2, 1, 2, 3, 1, 2, 4, etc. 1, 2, 6. And it turns out that the off diagonals, none of these are actually possible if you plug them in. So you can do that on your own. There won't be any solutions. The way you can think about that, for example, is that you know, if you do like I don't know, pick one, like a 1, 2, 3. So I have no spinning about one of them. I have a twofold spin about the other. And then somehow I'd have to have a threefold spin around the other axis that would be compatible. And of course it can't be because you'd need to have another twofold axis, right? If you can't get the extra symmetry out of it, right? So it turns out that the off diagonals aren't going to work. But if you look at the on diagonals, you have things that you can believe. And I guess I'll tell you a priori do work. So we don't have to do all these. So you could have a 2, 2, 1, a 2, 2, 2, a 2, 2, 3. And certainly you can see 2, 2, 2 can work. I could have a 180 around one axis, another 180, 180. We just have to figure out how far apart they are. And so it's going to turn out that the diagonal of this matrix is where all the possible solutions are. And of course, not a lot of them are in there either. So after all this work, it turns out with this in a generic case, there's actually not that many choices really that we have to add here. from Eulers Construction. So like I said, we have our basic set, which is a trivial case where there are no other axes actually. They don't rotate at all. So that's going to still be, valid. And then we're going to pick up a few through this center aisle. As usual, I go through this and tell you, we're only gonna, it's kind of, when you just inspect it, you can kind of say, well, obviously the diagonals have A and B having the same rotation, and so you can believe that that's going to be more compatible. And indeed, all the solutions show up on there except for one. And there's going to be one that exists off the diagonal. And it's going to be actually, let's see, 2, 3. There's going to be one solution. Of course, that means it'd have to be on 3, 2 as well. There's going to be one solution off this diagonal, and all the other ones are going to be along here. We could go through this, but for time reasons, you can play with that if you want. But I think you can see the basic principle of what we're talking about here. Eulers Construction allows you to have a set of equations that if we fix two axes, it defines then whether there's real angles between the axes, and it defines how far apart they are. And so that is the point. And if you plugged into all of these guys to look at what axial combinations are compatible in C with stuff we chose for A and B, and how far they all away for each other, this set of equations will give you real solutions. And we told you that these are the trivial ones, which we are already going to know about. And then all of the other ones tend to be that you have to have A and B be the same. And then that allows particular combos. And there's a unique case where we're not like that, which is the 423, which is a cubic symmetry, and a very important one. So we'll now go forward and actually we'll do some of these. We'll build up from where we are right now using this to pick out the few axial combinations that have to be rules for the point groups as we go up towards our crystallographic point groups, 3D.